Sorry, go ahead, Wei.
No, I mean, people will get busy and busy after midterm, so. computer doesn't have philosophy, and there is no way to do a live demo. But I don't know for this type of instructors forum why they want to do. Oh, they say asynchronous teaching tools.
Huh.
So.
Oh, interesting. Okay. It'd be interesting to hear what they have to say about that. That's sessions here already doing stuff that the other folks want to do.
Mm-hmm. So that means they probably find a lot of repetitive questions. So people can reuse whatever they prepared.
Yeah.
Okay. But as I mentioned, I met that like a very nasty patron through VREP. That person shouted at me and saying like, I just want to ask a reference question. Remember that one? So that guy saying, I searching, I think in a historical English paper, and that patron, hi, are you coming
Hello.
to the club? Yeah.
Excellent.
Hey. Welcome.
You're the first one.
Oh.
Jeremiah said he'd take care of that.
Okay.
Thank you for coming. Today we are going to do data engineering in Python with polars and pandas was the official title of today's meeting, but there's going to be very little pandas, but quite a bit of polars and a little bit of data engineering. So we have our Jupyter notebook here at this link, and it opens up to this. So I changed the title of this notebook to be somewhat more indicative of the contents of today's session to get rid of the panda stuff. So if you have ever done any kind of data wrangling, cleaning, manipulation, whatever you want to call it, in Python, you've probably used pandas. In this workshop, we're going to use, or at this meeting, we're going to use polars instead. Polars is a newer library than pandas, and it brings a couple of key ways of thinking about how you deal with data that make it a better option than pandas, especially for very large data sets. So namely, what it is extremely fast. Whether it's easy to use, that's more, I mean, none of these are easy to use, I don't think, for someone who has no experience with them, but, and it's open source definitely, but it is allegedly, according to them, of course, extremely fast. And if we get time to talk about lazy loading and things like that, then that shows even more how quick it is. So this is a comparison with a bunch of different similar libraries. So pandas, so what polars can do in 8 seconds takes 207 seconds, which is what, almost more than 3 minutes in pandas. PySpark and Dask, which are distributed ways of wrangling data, are much faster than pandas. We expect this, but this speed that polars can give is astonishing. And I'm not entirely sure why it does it, but I'll explain a little bit of that in the notebook. So the use cases for pandas are basically the same, but it's not a drop-in solution. The API looks rather different. In many ways, to my eyes, the API is similar to dplyr if you come from the tidyverse, but otherwise, polars is written from the ground up in Rust, so the actual thinking happens very close to the machine. In Python, very often the libraries will have sections that are actually written in C that are also close to the machine, but Rust is slowly moving C out of the picture for these sorts of things. But yes, so blazing fast performance even in comparison to PySpark and Dask. And then it has lazy loading and query optimization. So what that means is that you sort of have a workflow that you create ahead of time and that you don't execute on the entirety of your data until you're ready and you know that this is what you want. And only then do you actually execute the query and then read everything into memory, et cetera, as opposed to in pandas, if you have df equals blah, 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 then df equals df dot blah, 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 then df equals df dot blah, blah, blah. then that entire data frame keeps being in the memory and becomes resource intensive. So this isn't to say that Pandas is useless. Pandas has in some ways a more intuitive isn't the right word, but maybe because many of us have used it for so long, it's just a little bit easier to wrap our heads around. And one thing that Pandas so far in my experience does much better is things like the apply function, where you apply a function that you wrote, an outside Python function, you apply it to every row in a data set. Polars doesn't really do that well. It will let you do it, but it will complain a lot because doing that breaks its optimization. It can't do the optimization appropriately when that happens. So this is all in the context of ETL, which is one of the aspects of data engineering, and perhaps for our purposes today, the most important. ETL stands for extract, transform, load, and it's a kind of way of thinking about moving data from one place to another. So people who work with data are often people who are using data at the target side because they want data that is already quote unquote clean or prepared in a specific way so that they can spend their time doing analysis. Whereas the engineering part is taking the quote unquote raw data out there and preparing it for the analysis. So it's two separate steps. Frequently, probably for every one of us here who has ever done research, we have had to do both sides of that. But at a massive scale, that becomes two specific jobs, basically. And if you get a data science degree, for example, like, well, I can speak to the Masters in Data Science program here at Columbia, we do a lot of analysis side. So whatever happens after this flow chart. And really, we only have one class of the 10 we take that is focused on this part, which is the systems class, which is about databases and about using things like Dask and PySpark. So yeah, so let's get into the code. Oh, all this time I was not showing my screen. That's too bad. So here's the flow chart for everyone who is watching on YouTube and missed the flow chart. The rest is just text. Anyway, so let's get to code. We can import polars. Oh, so in the Google Colab, just do shift return to execute the code. I think just like in Jupyter, but I can never remember. And we'll start with the polar syntax. So polars breaks up its syntax, and this is where things may start to look a little depliery, into contexts and expressions. An expression is a sort of a mathematical expression of some sort that involves something that happens with columns, with columnar data. Polars, I'm not 100% sure if this is true, but I think polars is more focused on columnar data as opposed to row-based data. Is that a distinction that's clear to everyone? Like what I mean by columnar data as opposed to row-based data?
So my understanding is they just put everything in the same column. So that's how to save the space and compress the size.
Yeah.
But for the regular data frame we talk about in Pandas and R, it's both row and column, right? Then that takes your memory and processing time. So that's a key difference about why polars are very efficient.
Yes. So this is a little bit noticeable in the file formats that we use. So polars can read anything, but I, for example, over the last few years have gotten out of the habit of using CSVs for anything, especially like I'm working on a project now where we're dealing with data sets that have 41 columns and 3 million rows. Mm-hmm. And something that when you start getting that big, it makes sense to stop using CSV and start using which is row-based, because the CSV gets read in line by the parser, and instead using something that's column-based, like Parquet, specifically Parquet. And that gives a space savings. Parquet files, I think in this project I'm working on, Parquet files are typically 20% the size of the CSVs, the same exact data. But columnar data has a strict requirement that the type of each column has to be determined ahead of time. Or not, well, it has to be determined. So if you have a column set as numbers, then it's always numbers. It's not, and Pandas is mostly like this, but I'm not sure if Pandas will complain as much. CSV definitely will not complain. CSV has no idea what a data type is. So
CSV is basically text.
yeah, it's just text, right. So the benefit of the columnar data set is that it's stored by column. So doing column-wise operations like sums, means, anything like that, or filters based on values in a single column are much, much cheaper because it doesn't have to read the whole row in every single time it goes through. It can just look at the column and execute. So that's something that you see here in something like this first expression. So I have this thing, tip percent equals PL call. So that's just the Polar's column name tip amount divided by PL call fair amount. And you can see here that PL call is referencing a specific column in a data set, but no calculations have been done. And in fact, we don't even have the loaded data. If I were to do the equivalent of this, well, I would need to have a data frame. But there's no real way to do this in Pandas that I know of. But this is the equivalent of kind of creating a query ahead of time before you actually execute it. So let me execute this. And we actually won't use this quite just yet. It'll come up later. But it's this kind of idea, like you'll notice that this is PL call, not DF call, because it's not a reference to a column in a specific data frame that has already been instantiated. It's just saying Polars, at some point in the future, there's going to be a column called tip amount and a column called fair amount, and I want this thing called tip percent that's dividing the two of them. You can probably guess what those values are, but let's actually load some data. So this is my sort of the data club favorite is using New York City taxi data. So this is updated with the latest data that they have available, which is August of this year. And you can see here that the syntax is somewhat like the syntax for Pandas. It's just pl.readParquet. There we go. And for me, at least when I was doing this, this isn't, I don't know how much of this is, actually, let's have some fun. Why not? Like I don't think that this is a function of Polars that reads it in 3 seconds. Yeah, okay, I didn't think so. But that's 3 seconds to get this data frame into memory is really quick, whether you're using Pandas or Polars. And I'll show you why in a second. Because if we look at the shape, we see that there are 20 columns, and this is 3.5 million rows. So how was it able to load only in 3 seconds? So it's downloading from CloudFront. So CloudFront is going to be fast anyway, especially with for static assets like a data set that doesn't change. And also in part because the file itself is smaller because it's a Parquet file as opposed to a CSV. So again, like I said, the Parquet files that I've been looking at, like I've been converting CSVs to Parquet files and routinely getting files that are 20% the size. So,
Open data?
yeah, this is from, oh, sorry, this is really unclear. I think up here, yeah, New York Yellow Cab trip data.
So that URL link is also from this
Yes, it's just what you get when you click here and go to August yellow taxi trip records. So these point to CloudFront URLs
Okay.
to speed up the access.
So did you try to open them in the web browser when you firstly,
If-
for example, I think I'm interested in, I want to know what it is, then we just click on it.
Well, now it's downloading it, but I don't, what you want to know about the data, like
I
the
mean the
data?
link. So where
Oh.
did you get that data link?
Oh, I
Because
just,
this is the local file.
yeah, I just copied it
Okay,
from
okay,
here.
Okay, good.
Yeah. Sorry, you can see down at the bottom of the browser.
Because
Down
you
here.
mentioned the downloading through URL is
Achoo!
faster than the local folder file, right?
Oh, I don't know about that, but I mean, maybe.
Yeah,
Okay, so, and then if we look at the columns, there are 20 of them. Here they are. And if we look at the head, so this is just like Pandas that shows the first 5 rows, or first 5 rows, we can see that this looks a little bit different than how this would look if we did this in Pandas. Let's, why not? Because I have the Pandas loaded. So what do you notice as the big difference?
It has type, like data type. Also.
Absolutely, yes. So it is working with it explicitly advertises the data types. And whereas here, we actually have no idea in Pandas if these are date times or just a string or whatever. And it also conveniently gives the shape here, although that's not particularly helpful because we already know that it's only going to be 5 rows. So it's sometimes I have to remind myself that this isn't the shape of the entire data set. And yeah, so otherwise it's Colab is providing the extra cuteness of the stripiness. But yes, but we get these data types. So I find that to be helpful because sometimes you end up with wild things. So the context is the next part. So we've been sort of talking about expressions so far a little bit, but we'll get back to expressions. So there are 4 that we'll talk about: select, with columns, filter, and group by. So I'll start with select, and select works exactly like in dplyr or a select statement in a SQL database, like select star from. So where we pass it a list of columns. These are the only columns that we'll be using today. And so I reassign df equals df select. So now we just have these 6 column names. So it'll make for prettier images. Now, there is this somewhat clever thing that we can do here. So I commented out this unnest on the next cell. I just commented it out. And now if I run this cell, we get the value counts for passenger count. But we see that the data type is a struct, which is sort of like a tuple or a dict. And so what df select passengers equals pl call. So here, passengers is the column name. So df select, create a new column. And that column for its value will have pl call passenger count, so the passenger count column, execute value counts on it, and then sort it as true. So it gives us the number of passengers and the number of rides for each passenger count. Now, the shape is 11, and it only shows the top 5 and the bottom 5, so we can see 0 is missing here, so 0 is probably in the middle here. And the struct type I said is like a tuple or a dict, so actually if we unnest it, we get two columns. So we get the passenger count, the original passenger count, and then the value count. So this is a way of, and I don't know that Pandas does this because I only ever use value counts as a way to print information to the console, like to print to the Jupyter Notebook to tell me these kinds of things, whereas this returns a data frame. So I could conceivably just feed it into something else, and I have passenger count and count. So this is the original column, and this is the summed value. So another way to think of this is as something like a pivot, because it pivots on passenger count, and then for each value of passenger count, it does a sum. And what's peculiar here is, why is the second most common passenger count null? I have no idea. There may be some kind of correlation based on vendor ID. So one of the columns I got rid of is the vendor ID, which describes different ways of, I think, the different companies that have the little meter boxes. I'm not 100% on that. But for some reason, almost 900,000 of the trips 2 months ago had null for their passenger count. Also surprisingly, 0 is in between 4 and 5. So I don't know if that's just that many burrito taxis, like over 10,000 burrito taxis a month, but somehow 0 is a very common passenger count as well. So we have these contexts. So we've seen select, then there's with columns, filter, and group by. So I'll just keep working with select. So we can select in a SQL context. You usually do select star from, or select just a couple column names from, and then you do where, et cetera, et cetera. And that sort of exists in here, except it's a little bit more, where sets up conditions, just like it, and we'll see where clauses here in a little bit. But this does, I'd have to think about how to do this in SQL, because it's not immediately obvious how to do it within just a select statement. But here we're saying df select, so take the data frame and select a column called trip duration. Now this column does not yet exist, so it will create it. And trip duration, and the value of trip duration is the column of drop-off date time minus the column pickup date time. And then select a column called distance, which is the value of distance is the column called trip distance, and then show the top 5 values of that. So we have, or just the first 5, not the top 5, the first 5 values. So we get a duration, the first trip in the data set is 19 minutes and 57 seconds, and the distance is 8.44. I can't remember if that's kilometers or miles. 8 miles in 20 minutes seems not very likely, but maybe. And that's that. So it did math and created these two new columns. Now, if I did df equals df select then the entire old data set would get clobbered and just have those 2 columns. So lose all the other previous columns, like what I did up here with df select when I clobbered all the other columns and we only ended up with 6 columns.
You see the time is midnight. So,
Yeah, the pickup time is
so it can be wired.
Oh, well, but the pickup time is 12:52 in the morning.
Yeah.
And these aren't necessarily, well, this is refers that, yeah, they aren't necessarily sorted, and we'll see fun stuff about the date times in a bit.
That was my question, like, it was sorted by this aggregation, just in the order of the data.
Yes, so far it's just in the order of the data. We'll get to sorting in a little bit. So I think properly speaking, it is, so we sorted here with the value counts by doing sort equals true, so the highest count was first, but we haven't done any proper aggregation yet. That will come. Okay, so similarly, we can do the same thing, but instead of doing head, we can ask it to describe. And what you'll see here is if you do something like describe in Pandas, so df Pandas, not trip duration, trip distance, describe. We get, is this also a data? This is probably a series where we get a distance and then an index for each. Yeah, this is a series because it has a type of float 64. Okay, so this is the same thing except we get a different, it looks different because we get 3 columns. We get a statistic column and, we were asking for 2 different things. So we get a statistic column and then the 2 things that are being described. So it's not as different as I thought it would be from the Pandas example. I forgot that Pandas gives a data frame as well, or a series, or both. Anyway, so we see that trip duration has no nulls, but the standard deviation is null. And I remember figuring out why that's the case, but I don't remember why that's the case. Maybe, no, it is aware of these things as being dates, which is why it can calculate a minimum, or a duration of time, which is why it can calculate a minimum of -1 day, 20 hours, 31 minutes. So that taxi trip went back in time.
I think
Yes.
that's because this column is string.
Oh, the response is a string.
The duration column is
Trip duration is a time in milliseconds that it prints out conveniently for us like
Right.
this.
But why, when you do the summary statistics here, it becomes string?
Because in order to write answers like this, those have to be written as strings.
Okay.
Yeah, that's a little bit confusing. But yeah, because these are only the responses.
Right.
The fact that this is a string is not reflecting on trip duration itself as a string. That's confusing.
Because if you look at the count number, actually they are the same, right? It's just because it's a string.
Yes.
So the number will look the real number and the other will be the scientific.
Right. So it has to convert this number into a string, which
This
it,
is the polar thing.
this
They
is Polars
automatically
is doing, yeah.
convert it.
yeah, great. And the maximum taxi ride was 7 days. So this data is the best we've got, but is maybe a little bit unreliable on the edges. Anyway, we can do more things. So here we see, and this is a lengthy journey into, that's a good segue actually about how this data can have problems. Because if we do df select and we add tip percent, which we defined at the beginning, and we do mean tip percent equals tip percent mean, so we just, tip percent as a Polars expression has the method mean, which calculates the mean across the whole column. If we do this, we get nonsense. The mean tip percent is nan, so not a number. So why could that be? There's a hint if I scroll back up and, go ahead, Wei.
Because it's paquet, so you cannot indicate, you need to indicate that piece of thing to extract it, then make it as a thing you want to calculate. But in Pandas, they will automatically know that's a column you can calculate.
Close-ish. I would look here and think about how tip percent is calculated by dividing the tip amount by the fare amount. So how could this come out to be not a number, this calculation? That's a question. What could happen that would give not a number here? tip amount is typed as a number, and fair amount is typed as a number. We can see that here. Fair amount is a 64-bit float, and tip amount is a 64-bit float. So how, with two numbers, can you get not a number as the response if you divide them? Nope, it's not missing. Yeah, the denominator is 0. So that means that there are taxi rides that have fare amounts that are 0. So if one fare amount is 0, then that breaks infinity, like makes it infinity, and then the entire mean calculation is broken. So
The number 0.
the number 0, yes. So often in things like dplyr and whatever, and maybe even in polars also, but not in this case, it will often drop nulls right away when calculating things like means, precisely to avoid these kinds of problems. But these aren't nulls, these are zeros, and if there's a 0 in the denominator, then there's a 0 in the denominator. This isn't a data error. It may be the case, let me rephrase that. It may be the case that the machine is lying when it said that no fare was charged, or that there was some kind of error in transmission or something like that, but this isn't a null. This isn't a -1 or a 99 or something like that. This is just a 0. So we have this problem. So if we, what is the difference that I did here? Did I just change the order? Yes, I just changed the order. So if we ask to describe the tip percentage, oh, I think I was just being silly here with this tip percent equals tip percent. Or no, I had to do this because tip percent is not an added column yet to df. So if we do this, we see that there are no nulls, so there's no missing data in tip. Wait, this is for tip percent. We want to look at fare amount. So there are no nulls in the fare amount, but we can see that the minimum is $-1,143. The maximum is $2,000. So there are negative numbers, and if we do filter instead of select, and we do filter fare amount equals 0, then we see that 1,444 of our records have a fare amount of 0. So all of these records, when we calculate the tip percent, will be not a number. And then, or when you calculate, and so as a result, when you try to take a mean of, that's what I was getting at earlier. Like dplyr, I think if you take a mean of a column that has NAs in it, it will just drop them and will give you a mean of all the legitimate values, whereas this will not, because it will just continue propagating the not a number. So there are a couple ways to get around this. So for example, we can do something like add 1/10 of a penny to every value of fare amount, and now we get that the maximum fare is $2,092.50 and 1/10 of a penny. So now every 0 in the fare amount would become 1/10 of a penny. So to move further, so select kind of reduces the data frame. Like you can use select to add new columns, but it does not return the data frame as a whole normally. Filter does normally return the data frame as a whole unless you put select in front of it, but filter returns all of the columns but doesn't necessarily return all of the rows. Select will return all of the rows but not necessarily all of the columns. With columns returns all of the rows and all of the columns plus more columns. So one way of doing this is if we do df with columns, means take the current data frame with those 6 columns that I selected earlier, add a 7th column called, or create a column called fair amount, whose value is the already existing column fair amount plus 1/10 of a cent. And then from the whole data set, select that new column fair amount, create a new column called tip percent, rename the column trip distance to distance, and create a new column called mean tip percent that equals tip percent mean. So I know that's a bundle, and it's doing intentionally 4 different things here to show the different kinds of ways of doing the syntax. And tip percent, just to remind you all, is the expression that I set way up at the beginning of this notebook. And now we get something a little bit funny, which is that mean tip percent is the same across the entire data frame, which is expected behavior because we are asking for a mean of a column, and then we just fill in the mean in every row. It's sort of like extra space. It's taking up extra space because this would be an aggregation, but we haven't aggregated because with columns does not aggregate the data in any way or group or anything. It just returns the data frame the same way. So we said add a column at the end, mean tip percent, and just give them all the same value, which is the mean value of the tip percent column. Whew, that's a lot. Okay, so now if we do df with tip percent, if we do all this and then add df with tip percent at the beginning, we'll end up with an actual variable that now has the tip percent as its last column. So all through here, we were just doing these, executing these commands once, and then that these results disappeared into the ether because we weren't assigning it to any variables. We were just doing basically print. Like this is just a pretty version of print. Like if I wrap this around in a print command, come on. You know, it's the same thing except 1980s style. So like we didn't assign this to anything. So finally here we assign it and we create a new data frame called df with tip percent. And so this has our 6 columns, and then we added a tip percent column at the end, which is just the fair amount divided by the tip amount. And
With column means all the columns already, so you don't need to indicate those columns without change.
absolutely correct, yes. So df with columns only has these 2 lines here because we are changing the fair amount column to add 1/10 of a penny. And then we are creating a new column called tip percent, which has for its value tip percent. So this is the very dplyr way of doing this, where you are using column names as keyword arguments, which I actually don't use much anymore when I write polars. So there's another way of writing this thing, which I don't know if I do elsewhere here, but I'll do right now. You want to say something, Wei?
I mean, this is more flexible than the R dplyr because you define this pct at the very beginning as an independent line, and you didn't indicate that object is belong to this df, right?
Mm-hmm.
So in that way, dplyr will never recognize. You need to mutate under the df to do that. So for example, if you write syntax here using the within column, you probably need to say pct equal to that like a formula, rather than just say, oh, I have defined it before.
Yeah, so that part is more flexible.
Mm-hmm.
But in terms of the one of the things that was hard for me with dplyr is how sort of when you do like a mutate or a select, then you automatically have a variable group defined that is the names of the columns. So, and whereas here they show up as keywords. This is just like a little bit weird to me because how does the function know ahead of time that there's a keyword called tip percent? It doesn't.
Right.
And so the way that I do this typically now is I write out my expression and then I add the method alias afterwards. So this is identical, It creates the same exact thing as this does, but is just a different way of defining the column name with alias at the end as opposed to column name equals. So it's, I don't know which is better. I know that ChatGPT will use both. What's that?
The first one is more human being, in my opinion.
You think this
Second
is
one
this
more computer.
yeah, it could be. I think so.
If
The
it's for layperson, what does that mean?
well, so but this one's a little bit more sequely because you could do something like select blah blah blah, and then select fair amount plus 0.0001 as fair amount. So yeah. But this expression, I mean, I'm not good enough at SQL to know how to write expressions ahead of time and then reference them. But yeah. Okay, so then we have the head here, and yeah. So alternatively, we could, so adding 1/10 of a cent to all of the fares is not a big deal and cheap, and not cheap in the sense of computationally cheap. But we could have been a little bit more clever using filter. So for example, if we do df filter, and then we ask wherever the fair amount is not equal to 0, select it, calculate the tip percent, trip distance, and the mean. I just keep adding trip distance here just for laughs, basically. But if I do this, then I get a much different mean value. I mean, this makes perfect sense, but it's a little bit, it's a big difference. The mean tip percent up here was what, 30%? Whereas if we drop out the fares that are 0, then it's just just over 15%, which sort of suggests that people just tip 15% and a couple people tip more maybe. I recall seeing last year a distribution of tips, and it was stepped in the way that it looked like people tend to tip whole numbers or easy fractions or easy percentages. People don't round up to the nearest 10 or something like that.
Because it's touch screen, you just pick that percentage, right?
Yeah. Alternatively, we can do, if we can use the when expression, which is just like in SQL. So df with columns, fair amount equals PL when fair amount equals 0, then fair amount equals 0 plus 0.001. So only add that 1/10 of a penny to the fares that are 0. Otherwise, fair amount just stays fair amount. And then when we do everything again, we get back effectively the 30% we had earlier. So whether this is a more correct answer or not is left to the viewer to decide. We can also do things like filter by dates, and this is helpful because we can use the fact that these are date times to do things like say, show me everything that happened on August 10th. And show me the pickup time and how far the trip went. And we can also use fancier methods like isBetween to get trips that happen between 2 times. So this is between 11:58 on the 10th of August and 1 minute after midnight on the 11th. And we can see there are 5 such trips that fit in that rather narrow time window.
And you use head. If you don't use head, will you only have 5?
Oh, thank you. See, I told you I forget that all the time. You're right, let's do it without head. 139, I knew 5 seemed a little bit small. So 139 is a much more reasonable sounding thing. And we have here the mean trip distance is 5.98 miles maybe. The max trip distance was 22 and the minimum was 0, which is better than a negative number, but yeah. Finally, we can group data using group by. This is pretty much exactly like you would use it in dplyr or in Pandas. So we can get some summary statistics aggregating by passenger count. And then how are we sorting here? We're sorting by passenger count. So we can see that the burrito taxis made up 17,000 trips in August, were burrito taxis. Traveling on average 2.7 miles. So it's pretty far for a burrito to go. And the average fare was $17, which is an astonishing, that's more than the burrito cost, both the restaurant and you. And then we can do other sorts of things here. So with date times, you can do a group by dynamic where you can group by a specific chunk of time. So we can aggregate by every day. And we can see that, and this is where I said things get a little funky, because we have 15 trips that began on the 31st of July, but presumably went over midnight and ended on the 1st. But that suggests that the data includes, the August data includes trips that began in July, but is that all trips that crossed the midnight barrier? Because it's only 15 here, but we had 135 when we looked at the other midnight barrier. So I don't know. Or if there's some kind of hiccup, one or another, 2009 January 1st absolutely does not fit in the data. And there's only one such. And then there's one that's September 1st, that the trip, so this is pickup, so when the trip starts was September 1st. So unclear why that ended up in the data, but these are 17 rows out of, what was it, 3 million or something? So they can just be tossed. And that's about it. I said we are low-key EDAing here because all this, I wasn't writing these to variables, so I was doing the extract was just the first read parquet command. This was more the transform, and then, but I never did the load because I never pushed this data on to the analysis team to do stuff. I was just showing the different ways of working with contexts and expressions in polars. But that's about it. So that's what the first steps of data engineering look like. There are books in the library I think that we have access to for free. Don't quote me on that, about data engineering. You can read more about it there, specifically about how it pertains to things like data lakes and data ponds and data warehouses and all these different aqueous metaphors. They call it a data mart. I don't know what that is. It's like a store, a shopping mall with data. Who knows? So we didn't cover the loading part, so that's why it's just low-key ETL. But yeah, the polars, the more I use it, the more I like it, and it's perhaps maybe a little bit more verbose than Pandas, but I think that some of the Pandas syntax inside the brackets can get a little bit obscure. The iter rows, polars really doesn't like it when anything inside of here is not a built-in function. So if arithmetic is fine, but if I were to write a function that calculated the average and, you know, like a function called like mean and did mean actually, let's do this. I have a minute or two. My mean. So I will just do x. Oh, this was a good idea until now. I don't remember exactly how I should be writing this. So because I don't know what data type x is, x will likely be a, actually let's just try this. Let's try return x mean. Oops. And let's just do come on, my mean to percent. Okay, that worked. So now let's do, all right.
Standard error, something like that.
No, it maybe works because I'm only, the point is if you introduce external functions, external is in outside of polars,
Yeah.
like you do your own kind of apply functions where you're doing things like the lambda function in Pandas's apply, you can put anything you want in that lambda and it will receive either the value of the column that you're applying to or the whole row that you're applying to. Here it will complain. It will say, please don't do this. This is very inefficient. The whole point you're using, it says that. It says, like, effectively, the whole reason you're using polars is because you want efficiency. This breaks the efficiency.
So only use polar functions.
Yes, you can pre-auth.
Is there a page on polar website?
Oh yeah,
where
for
you
sure.
Have that.
Yeah. Let me actually see. User-defined Python functions. So this is what they're talking about, is that the polars expressions, yeah, there's less need for custom Python functions, but sometimes you may need one. And if you do pass one, so as soon as you're using map elements, this is a tip for all of you using ChatGPT. ChatGPT loves to suggest that you use map elements. It'll work, but you might as well just go back to using Pandas because any of the speed benefits you get, you lose as soon as you do map elements.
Yeah, use the define.
Yeah. Oh, this is actually a good example. Right. So this is using math's built-in log, and it works, but it says here there's a performance overhead because it has to take every value and calculate the log as at a time.
The math is a different library.
Math, yeah, so that's why this worked, is because it's using math log. So it takes, it wasn't going to work for me because they were using map elements. So this is a little bit like apply lambda, so it sends the value of values. This is confusing. It sends the value of values to my log, which then uses the external math, well, the built-in math library, but it's not a polars library, and calculates it. And that's fine, it works, but like it says here, it has two problems. So it's individual items because you can only work on one column and you send every single value at a time. And there's the performance overhead because you're working outside of this. So one option they have here is to batch. So this is like using NumPy where you can like to vectorize the calculation, or like in R where you always want to vectorize your calculation so it's not doing this iteratively. And so here they suggest using nplog instead, so that would be one way that's faster. And then they might not have a built-in log function in polars. So here are, under expressions, here are all the different expressions you can do. There are many, many, many. There's a lot of, you can have a data type of a list, and so you store the whole list and do all kinds of manipulations on the list, which can come in handy, you know, like for the names of all the kids. So this is in lieu of having a relational table. You can create categories, so those go super quickly because it's a fixed set of categories. Structs I showed, they act a little bit like tuples. Windows and folds I don't even understand. And then you can feed in NumPy functions, which will go quickly because, again, it vectorizes it. And that's it. The last thing I wanted to just really quickly say was just that what we didn't look at was the lazy API, which lets you keep the data out of memory as long as possible. So this is where it really feels like using Dask or PySpark, because you are you're basically creating your whole query routine, and it will even you can even get it visualized. to see the optimization. So this is like the badly optimized. It's doing these three statements in this order. So it scans a CV, then it does these other things. Whereas when you optimize it, it combines it looks at what you're trying to do and figures out what the best order actually is to do what you need to do that will be most optimized. And then when you do that, it will be able to use less memory. And then if you also do it while streaming, instead of reading the entire file into memory or the entire data frame into memory, it will just do magic to work on it and parallelize it, or however you want to describe it. So yeah, so that has saved me, because I've been working with gigabytes and gigabytes and gigabytes of data lately that is just nukes my computer. Forget it, I don't have enough RAM. But working lazily and in streaming mode helps with that. That's it.